I'm Dean Wampler. I've been doing big data lately. I work for Think Big Analytics, which is sort of a Hadoop-oriented consultancy, and this is mostly a rant about what's wrong in that industry. So the first thing I should probably define is what I mean by big data. And it's one of those buzzwords that all the suits are throwing around, and they're throwing money at it. But for me, what it really means is this data that's so big, for some definition of big, that traditional solutions, relational databases, whatever, either they're too slow, they're too expensive, or maybe even too small to handle the computation. And of course, great examples are like, all of Facebook's privacy data that they know about you, and Google's indexing of the web, and so forth. So those are the kind of the things that set apart big data and have kind of forced us to go to new solutions. And the biggest one right now that everyone's talking about is this open source project called Hadoop. And just briefly to explain what that's about, it's really two major pieces. One is this so-called MapReduce engine for distributing computation across a cluster, where you break up a job into tasks, and those tasks are oriented around a mapper phase and a reducer phase, inspired by the map and reduce concepts we're used to from functional programming, but somewhat bending the rules a little bit. And then underneath is like a distributed file system, so you get replication and also distribution of computation and that sort of thing. And basically, I see three trends kind of happening in this industry that are relevant to this discussion, and the areas where I think we're letting too many old ideas influence the thinking rather than embracing mostly functional programming and certainly languages like Scala to make these industries work better, for us as developers. And the first one is the one I already mentioned. Obviously, data sizes are going up exponentially, they say, although of course nothing can grow exponentially forever. Certainly the big guns like the Twitters, your Twitters, your Facebooks, so those kind of people are obviously got a lot of data. But even smaller companies now are recognizing they have some useful data. They might be drinking the Kool-Aid a little bit about what they can get out of that data in terms of useful information, but nevertheless they're concerned about making better use of what they have, because sometimes it is a really useful, reusable asset. And if it's essentially free, for some definition of free, to keep all that data and to play with it, then you never know what will come out of it. And I'll give you an example of a project I worked on recently. A major networking company in Virginia wanted to keep the traffic that they accumulated over the past year, so they could go back and do retrospectives when customers reported problems. They could replay what happened and discuss the problem. They could do long-range reports and trending, stuff that was much harder with their current infrastructure. The other big trend, though, is that the notion of formal schemas, really kind of nailing down the model of your data, is kind of becoming much more relaxed, because we realize that in this chaotic world we're in, we have to be flexible about data structures changing from day to day, trying to integrate disparate data types and so forth. So people need more flexibility and less rigor in the usual way that we used to do things, of modeling it all up front and knowing exactly what we have and then having to shoot a DBA if you wanted to make a schema change. Which reminds me of the joke, what's the difference between a DBA and a terrorist? You can negotiate with a terrorist. But I think another cool trend that you've probably heard a lot about is the whole sort of rebirth, if you will, of artificial intelligence and machine learning. Obviously, a lot of the stuff that's happening, in particular the idea that you could get gold out of your data, is kind of driven by machine learning. This is a picture of Stanley, the car that was built by Google and some researchers at Stanford, that was the first self-driving car that negotiated a desert maze as part of the DARPA Grand Challenge a few years back. And I think this car is now in one of the museums in Washington, D.C. But I mention this in particular because there's some sort of traditional machine learning algorithms that people are using for doing things like, how do I recommend the best movie if if I work for Netflix? How does Amazon decide that you bought a book on Scala, you might like a book on Clojure, maybe, that sort of thing. But I think there's also some interesting stuff that's happening with artificial intelligence. Like, for example, these cars, they might have maps of the world that they think they're in, but they also have to do a lot of highly iterative, highly data-driven algorithms to actually figure out where they are on that map. And there's some really cool techniques that they're using to do this. And I can see that some of these techniques will bleed over into some of these more traditional machine learning problems where we sort of more dynamically figure out the information that we want, decide what to recommend to customers or how to react to denial of service attacks or potential fraud events and stuff like that. And it's also kind of driving us more towards a model of less structure in our models and more flexibility in being data-driven and using some core structures and algorithms that can just react to the data to create the kind of emergent behavior that we want. I did the online Stanford AI course this past year that was taught by Sebastian Thrun and I forgot the other guy's name anyway. But in one of the lectures, they made the point that data-driven programming like this is sort of the ultimate kind of agile programming, where you don't really hard code a lot of business knowledge into your code. You let the data kind of drive the behavior. And I think this is also pushing us away from things like object orientation and modeling and more towards more fundamental data structures, fundamental algorithms, and building up emergent behavior that way. So a lot of us have built applications that sort of look like this in some schematic sense, where we might actually be querying a database, with SQL through some method, but then we turn around and pipe it through some object relational mapper, an ORM, and turn it into this grandiose object model in memory and then do other stuff with it. And I argue that this is totally unacceptable in a big data world because there's way too much overhead here, as well as this lack of flexibility I was discussing. That really we want something more like this, where we have this grand and glorious result set that's a nice set-oriented data structure with relations and all this stuff. Why are we kind of hiding it in some ad hoc model of the world? Why don't we just work with that data as God intended, I guess you might say. So we might have to do something to convert it into Scala data structures, for example. If you're a JavaScript programmer and you're using MongoDB, you don't even do that much. You just take what comes right out of the database and it's already in JSON. But nevertheless, we might have to convert it to our core data structures anyway. And then we can start doing domain logic stuff with those kind of data structures instead of our ad hoc models. And kind of another view of this of applications we probably all built is that when you have this rich domain model in objects, there's really kind of a strong tendency to put it all into one kind of big application and then have all of these feeders going into it and out of it, various web clients and various data services and so forth. And the problem with that model, in my view, is that it's harder to scale horizontally. It's less reusable. It just becomes this big wad of code that unless we're very, very diligent about keeping it well factored and all that stuff, it tends to agglomerate and become harder and harder to maintain and harder to evolve. And instead, we need to focus more on this, small, highly focused processes that can be glued together. And I think a lot of the technology that we've learned and developed in functional programming and in Scala in particular, like actor models, and the reliance on fundamental data structures like lists and sets and maps and so forth really makes it much easier to implement stuff like this. And that gives us the kind of flexibility we need, not just for big data, but for just general data problems. I often think back to a project I did. This would have been the mid-90s when I was working for a company that built tools for embedded systems developers. And I spent like 2 years working on a new UI in C++ for this embedded system tool, pretty much disconnected from reality, and eventually the market left us by, and that was a failed project. But I can't imagine spending 2 years on anything anymore. I can't imagine staying in the same job for 2 years anymore. Things move so fast. And for me, having the flexibility to just get it done, but to do it in a clean, elegant way with some fundamental tools is very compelling. So let me talk briefly then back to those 3 points, just to be clear about how I think this affects these trends. Well, if data size is going up, then despite the fact that we used to have Moore's law, and we still sort of do, at least if we scale horizontally, and we have disk size, or disk drive sizes that keep increasing, the data just seems to be accelerating faster than that, and we just really need to keep our processes as lean and mean as possible. And I think if you come from like the Agile community, there's this great catchphrase, what's the simplest thing that could possibly work? And you know, these days I don't think it's passing it through an ORM and converting that result set into an object model. I think it's working with the data as God intended and getting it through the system as fast as possible. And that also gives you a lot more flexibility. If I'm passing maps around, that's a lot more flexible than a class design that I have to tweak every time I have a new concept enter my domain. And also this idea of data-driven programs, it's a lot easier to connect algorithms and core data structures. Things like, you know, just the simplest examples are like our flat maps and our maps and our you know, for eaches and all that stuff. They just work across all of these core data structures that have these fundamental concepts, rather than having to re-implement those wheels every time we build an object model. So let's get back to kind of the key point of this talk, which is specifics of big data. And I want to talk a little bit about using Scala to do MapReduce programming in the Hadoop environment. And what I thought I would do is very quickly walk you through the hello world of the MapReduce ecosystem, which is the so-called word count algorithm. And the idea is very simple. I have this corpus of documents on the left, and I want to first find all the words in those documents, and then I want to count all the occurrences of those words. It's a very simple algorithm, not actually useless. There is some use for this kind of thing. For example, if you're building like an automated translator, a language translator, if you know word frequencies, that's a clue as to what language you're looking at when I throw a document at you and you don't know what language it is. Obviously, the word the is going to show up a lot more in English than it will in Chinese, for example. Not to mention the character encoding is a little different there. But so let's just, oops, that went a little faster than I expected, so let me back up. So I have, like, say, 4 documents, one of which happens to be empty for a reason I'll explain in a minute. And each of those will get in a mapper task in Hadoop terminology. And this is all key value based stuff, so what will happen is the mappers will receive, because this is the way the infrastructure works, they'll receive each document maybe with the document name. We actually don't care what the key is in this case. And then the contents of the document, the whole contents. And notice that for document 3, the contents are empty. And then the next phase is the mapper will output. Well, first, it's going to tokenize the documents in some useful way. In this case, I have it convert to lowercase. And then the most naive form of this algorithm is that every time it sees a word, it will output a key value pair, which is the word is the key, and the count of 1 is the value. So you can already see there's some optimizations you can do, like not spewing the network with, you know, the same word over and over again. But we won't get into those details. That's not important. And then there's this sort and shuffle process that happens where the keys are sorted, and then some algorithm is used to distribute these key value pairs to the so-called reducers. And the main requirement here is that for any given key, all values for that key will always go to the same reducer. You know, I don't want the word Hadoop showing up on 3 different reducers, so I have to either let the default algorithm figure that out, or in this case I hacked up a custom algorithm where all the keys that start with the numbers 0 through 9 and the letters A through L will go to the first reducer, M through Q to the second, and so on. And so you can see that, just to show the first example, out of the first mapper you'll get the key and value pair Hadoop 1, MapReduce 1, uses 1, and so forth down the line. And of course, now you see maybe why I had the third document in there. The word map is generalized here. It's not a one-to-one mapping. It's really a flat map. It's a zero-to-many mapping. But I guess flat MapReduce would not be as elegant a name as MapReduce or something like that. So anyway, it's not our usual mapper, but close. And actually what you get inside the reducers then is the key and then some sort of collection of all the values. Array list, I think, is actually the default implementation. And in this case, again, we're counting words, so all I need to write out at the very end then is each word and then the total count, and you can see all I have to do is sum the elements in the array. And usually this is tab delimited output by default. So that's word count. That's the hello world program you always do first. So let's actually look at what this is like to do in the Java API, which is essentially the assembly language of the MapReduce world. And then we'll talk about doing it in Scala. So I actually use Scala syntax, and I'm sure all of you guys in the nosebleed seats can read this very well. But, and it's obviously deliberately too small to read. And the tragedy is that, yeah, I didn't want to offend your sensibilities, but no, the tragedy is that this algorithm is actually not so bad in MapReduce. There's still a lot of noise here that I'll talk a little bit about. But as soon as you get to anything more complicated, like doing joins of data, you know, the typical database join kind of idea, it gets heinously ugly very fast. And one of the things that's ugly about this is, and getting back sort of to the general point, no doubt you can read where it says like long writable text, int writable. Those are like the input key values and so forth. And yet, why isn't it, what's this long writable? What's this text thing? Why isn't it just longs and strings and stuff like that we're kind of used to? Well, this is one of those examples where the API bleeds heavily into the code, and you have to use their own custom serializable objects, and you can't use your native types because it's not abstracted from you. And so when I started reading this code, I had flashbacks to the early 2000s in EJB 1 and 2 programming. And I'm sorry to bring that up. I know that's a bad memory for many of you, but unfortunately, this is a very invasive API, and it kind of breaks a lot of what we've learned about good API design in the last few years. And as much as many of us like to criticize Spring, for example, because we think it's kind of gone a little overboard, at least some of us might think that, nevertheless, Spring did us a great service around 2005 or so by showing us a much more elegant way to decouple the framework from the application logic. And I think that's what needs to happen here. So let's actually do that. And I'll start with a higher level API that abstracts over some of that gory detail called Crunch. And it's actually based on a Google paper that came out a few years ago about a Google project called Flume Java that exposes an abstraction of like parallel collections and workflows and pipelines of data, and the sort of way that you would typically want to think about the kind of problem that you're doing, not this low-level MapReduce stuff, which is not really the core essence of what we're trying to accomplish. And just to briefly give you a sense of what some of the concepts are in Crunch, and these are the actual Java types, we've got your pipelines, you've got your basic parallel collections, and then you've got these parallel do things, which is, don't we already have this in Scala? Why are we re-implementing the wheel? I don't want to criticize Crunch because this is actually a really nice toolkit, and the guys that wrote it did a great job. But it's really a criticism of languages that don't really understand data, that they have to, the developers are forced to invent concepts and always do it in their own unique way that should just be baked into the thinking of the language and the libraries as well. But anyway, we've got these parallel collections. We've also got parallel tables, distributed key value stores, and then we've got more operations and custom types like grouping tools that we already should have in our language. And then finally, there's even yet more types that represent the output of groupings and stuff like that. And by grouping, I mean like I want all the words to show up together and all the Hadoops to show up together and that kind of thing. So there's all this custom stuff that the Crunch team had to invent, but it does give us a slightly cleaner API. And this doesn't look that much smaller than the last example, but in fact, it is conceptually easier to see what's going on. There's less noise in this API. And when you scale up to bigger, more complex job flows, data flows, it actually kind of adds up to be much cleaner than Java. But again, for those of you that can't read what's on here, you'll see things like their own custom F2, or rather F1, that takes a string, returns a string. And as usual, it's an interface. You have to instantiate it, define all the functions in line. The word process would be the word apply in our case, and so forth. So there's a lot of boilerplate still because it's a language that doesn't understand data and the kind of things you want to do with data. But fortunately, the Crunch guys wrote a Scala API, a DSL on top of it called Scrunch, because all Scala APIs have to start with SC or S at least. It's a law of the land. Oh, and actually I wanted to point out something I forgot to mention, so bear with me as I back up for a second. So notice all the green on here. All the green are types, and all the yellows are function calls. So even if you can't read the words, and I deliberately did that, not to be nasty, but notice how much green over yellow there was. And now look at the Scala version, where there are very few types, not just because it's an inferred language. There really wasn't that much in the Java case either. If I, well, sorry, back up. If I had rewritten that previous example, which was Java syntax, if I had written it in Scala, it would still have a lot of type information. But now we've almost completely eliminated the types down to a few things that are inferred, and instead we have this sequence of transformations, this builder pattern where we're flat mapping that stuff, you know, here, and then we're filtering, is it empty, we'll get rid of those. We're counting things. This is basically our word count again. And we have not only a much cleaner API with less ceremony and boilerplate in our face, but something that actually fits the computation we're doing much more cleanly. And actually, this code, the number of lines here looks about the same as the previous one, but I cheated a little bit. I actually added stuff that I left off the previous slide, like the main routine. So this is, in fact, the entire program, except for a few of the imports that I omitted. All right, and it turns out that there's other toolkits. Cascading is actually a little better known, and if you use Cascalog or Scalding, which is a new Twitter API, you get the same transformation from lots of boilerplate down to here's the essence of the problem. So this is not anything new to all of us in this room, but basically Scala and FP are just natural fits for data computation. So I want to leave then with a manifesto, which is that we as a community really need to maybe be more active in bringing our brethren over, let's say, to the bright side. So I believe that Hadoop is the enterprise Java beans of our time. And as such, there's something out there that's coming down the pike that's going to be the spring framework of the big data world. That's going to make people rethink the way they write programs and do so in a much more elegant way. But we have the tools at our disposal to make this happen. So we already have an extremely powerful collection API, and we already have some support for distribution. You can parallelize the collections now. And I think the next logical step is to make them distributed in some way. And maybe the best way to do that is actually with Akka, because it already handles a lot of the infrastructure requirements for building distributed computation and managing resources and managing tasks. So this is sort of a manifesto and an invitation for us as an organization, or of people, I guess, to embrace that. And I hope that we will. And then the last slide is a shameless plug. It turns out my book is half off today, the ebook. If you go to the O'Reilly site and you want it, it's like $8.50. So what a deal. Come on. Come on. Do it. You know, help a brother out, all right? All right, anyway, that's it for me. Questions? Yes. So the question is, just discuss briefly the differences between cascading and Scalding and those APIs versus Crunch. As a matter of fact, I was thinking I would use examples from cascading and Scalding instead, but because of time's sake, I wasn't able to prepare those. But the programming model, namely things like pipelines of data and forking pipelines and grouping, they're very similar. I actually like the Scalding API a lot better. I think it's a lot more elegant and more concise in the long run. But the core concepts are very similar. And another advantage of Scalding and cascading would be that because it has a larger user base and a larger community, it's probably going to be better supported and better optimized. One of the benefits of all of these high-level toolkits and even higher-level languages like Hive and Pig that some of you may have heard of is that the developers can spend a lot of time optimizing computationally difficult stuff like joins, or a classic case where there's a lot of tricks you can do with joins depending on the nature of the data to make them much faster than they would be naively. Yes, sir. Yeah, so the question was, when I make this scurrilous claim that Hadoop is the EJBs of our time, am I talking about, like, if I can paraphrase, like the APIs or the core concepts or the ecosystem? I think it's a little bit of all of them. Certainly, there's already people are raising issues with the general MapReduce model. It is inflexible for some things. It's not optimal for graph traversal. Google has already started doing other work. There's a paper they came out recently talking about a new system they have called Pragle. And there's actually an Apache project that does something similar called HAMA, H-A-M-A, which is the model they're both using is something called bulk synchronous parallel processing, BSP, which is essentially a model of traversing through a graph like one clock tick at a time and updating the graph globally one step at a time. It's not unlike the way that a lot of older multiprocessing systems would work, where if you think about it, like if I have and in fact, like another good example of this, in fact, are like climate simulations and other numerical simulations where you put things on a grid. You might update every element of the grid at once with all the messages it just received, and then it sends out messages, and so everything's synchronous and updated at once. So I think we'll see both fundamental models emerge that are better choices. I think the API itself, if you've ever looked through the code, I mean, these are all very talented developers and they do very good work, but it's just full of incredible boilerplate that would probably, if they had done it in Scala or even Clojure or any functional language, it would be dramatically smaller and dramatically more efficient probably, because they could leverage some of the things that they just don't know about. I think that's the central problem. So I really think it's sort of at all levels. Yeah, but in the back. Yeah, so basically the question was pointing out a disparity with sort of the model that the collections and some other distributed systems use, where if there's a failure at some point, it just throws away everything and you start over. Whereas Hadoop, when it breaks up a job into tasks, if a single task fails, it will try to keep rerunning it up to a certain point, but keep the rest of the work so you don't have to start from scratch. I think that's the right model, that you try to recover as best you can, and that would have to be addressed in a real model, or anything that replaces it, let's say. So I don't see a direct one-to-one mapping necessarily between, like, say, distributed Scala collections and MapReduce or Hadoop per se. I really think it's more going to be along the lines of a replacement system that has to grow to address those problems. Yes, in back there? Yeah, so the question was that an attraction of Hadoop is that it lets Java people do distributed data programming that normally maybe not would have been able to use other frameworks, and that's certainly legitimate. Just a little backstory on me. I'm actually running our training program at Think Big right now, and so I train Java developers and I train people in these higher level languages like Pig and Hive. And I do try to teach the Java developers, look, I know you've always hated SQL and you've always hated DBAs, but you really ought to embrace Hive, which is a SQL dialect, and Pig, which is a data flow language, because they get rid of a lot of the boilerplate and then only jump down to Java when you need to. But that is definitely, though, a general appeal of this ecosystem. And one of the benefits of it, like one of the legitimate benefits of EJBs, was that they hided a lot of the complexity of distributed programming from you and took care of a lot of stuff like task coordination, like avoiding concurrency, or multi-threading, I mean, in particular. So, yeah, that's definitely an attraction. I just think we could do it in a lot better way. And I think I'm out of time. So I'll be happy. I'll be here all week. Don't forget to tip your waitress. And thanks for coming.